Here I'm going to do a classic separation of variables problem with a dielectric. So this is a sphere of dielectric put in a uniform external E field. Here's our sphere, radius r, dielectric constant epsilon sub r. We put it in this uniform E naught z hat external field. We'd like to know V and E everywhere, right? So we know we have a mental picture of what's happening, and that's that when we put this in the electric field, the external field is going to polarize the dielectric. We're going to get some positive charges up here, negative charges down here. It's almost like a conductor, except instead of canceling the electric field inside, it's probably just going to reduce it. And this is a problem we can solve with spherical separation of variables. So we start with our general spherical solution, and our next thing to do is to list our boundary conditions. So this is a great place to pause and practice doing that yourself. Our first boundary condition is when we go far away, we need the E field to be this, E naught z hat. And we already figured out what potential gives us this when we did our conductor in a uniform E field, right? We had the same E field, so we had this same boundary condition. And so this is the potential far away that gives us this E field. Just take the gradient if you don't believe me. And then, of course, we rewrite that in spherical, just like we did for the conductor case. And then, since this is spherical separation variables, it's nice to rewrite this cosine theta as P1 of cosine theta, because we know P1 of cosine theta is just cosine theta. Our next boundary condition is just that V is continuous at this boundary here. And this is something that we know is true for V. Always V is always continuous. So I've just written it in terms of the inside V, the outside V. So what we'll need to find is a separate expression for the potential in here and the potential out here, which is typical for a spherical separation of variables. Now we also have one more boundary condition at this surface, which we know that the discontinuity in E and then the discontinuity in the normal derivative of V is related to the charges on this surface. So see if you can write that boundary condition. So here's the boundary condition. This is really just D perpendicular above minus D perpendicular below equals sigma free, but then we've changed it to put it into the potential formulation where D equals epsilon naught E, and this here is minus E. All right, and then in our case, because this is a dielectric and there's no free charges in the problem, we can set this equal to 0. All right, so now we've got our boundary condition, so now we want to continue to solve. And we can start just by considering the inside and the outside separately. So here they are. The inside one we know can't have any B of L's, because as we go to 0, this would go to infinity, and if B of L's existed, this whole thing would go to infinity, which we're not going to allow. So this is just our typical separation of variables. Inside, where we have the origin, we only have A of L's. Now for inside, I've given the A of L's tildes just to denote that they're separate A of L's from outside, because outside we still have our entire generic spherical separation of variable solution, right? So we have some separate function for the potential inside and some separate function for the potential outside, and once we figure out what all these A of L tildes are and all the A of L's and all the B of L's, we will solve this problem. Okay, so that's our goal, is to apply our boundary conditions, figure out all the constants here. So this is actually identical to what we had for the conductor. The limit as r goes to infinity, our separated solution has to equal this E naught r P1 cosine theta from our boundary condition above. Because r is going to infinity, we can't tell anything about these B terms because they go to 0 because r goes to infinity. Then when we look at this, we can just solve by eyeball and see that we only have the A1 terms because we only have P1 of cosine theta on that side. So I wrote that here. We know that A1 equals minus E naught to match this equation. All the other ALs are 0. And what I'm going to do, because I have limited space here on the screen, is that I'm going to go up and erase this and rewrite this given this. And as we update things, I'll just rewrite up here. So I'm going to rewrite this up here. So here we go. This is our new V out given the new information we have. And that's from boundary condition 1. So then we just want to go on to apply boundary condition 2. All right, here, that second boundary condition is just that V is continuous at the boundary. And when I rewrite that, I just plug in R, and I have the inside equation for V equals the outside equation for V. So that's all I've done here. And then remember, my goal is to find these constants. And clearly I'm not going to just get an equation for them here, but at least I'm going to be able to relate the A tildes to the constants on this side, right? We figured out A1 and we don't know the B of L's. But you can see, because P1 is special, something different is going to happen when we're looking at the P1 term, or the one that multiplies the cosine thetas, versus any other term. So first I'm going to write what happens when it doesn't equal 1, and that's over here. So if L doesn't equal 1, then we have to match our, because remember, these P of L's are orthogonal, so the only way to get like a P10 would be to match all the constants for P10 here with all the constants for P10 here. So that's what I did. So this A tilde of L, R to the L, has to equal this B of L over R to the L plus 1, so that for any L that's not equal to 1, the say P10s match across the equal signs, or the P5s match across the equal signs. So that's what this is. Now the 1s, we just have this extra P1 contributing, so we have A1 R to the 1, the equivalent to this, but now it equals E naught R plus B1 over R squared. All right, so these two equations, I'm going to have to erase to make space, but we need to keep these two equations because these are what are going to help us moving forward. This is the third boundary condition here. Here I've just rewritten it. I've moved this onto the other side of the equal sign since it's equal to 0. And we know epsilon out is just epsilon naught times epsilon for epsilon r out, which is 1, right? Because so this is outside in a vacuum where epsilon is epsilon naught. And inside it's whatever the epsilon of our conductor is. And since we have epsilon r, this is really epsilon naught times epsilon r. But I've just written it as epsilon. And then what we need to do is we have these two equations here. We just take their derivatives and plug in here. So go ahead, that's really good practice. Pause and do that yourself. So here I've taken that derivative and plugged in r. And this is what I get. Plugged in big R, I mean the radius. And then the next thing I need to do is get equations very similar to these, right? So what I want to go through is match a eyeball, remember, with the Legendre polynomials. So first I would look at the L's that aren't equal to 1 and say, okay, how do I match term by term the Legendre polynomials across the equal sign? And then I could do 1 and I get 2 more equations that look sort of like this. 1 for L equals 1 and 1 for L doesn't equal 1. So again, what I did here is for L not equals to 1, I just matched these coefficients here for not equal 1. This one isn't coming in because we're doing all the P of L's except 1. So I'm matching this coefficient with this coefficient across the equal sign for any L that isn't equal to 1. And then L equals to 1, the only difference is now we do have this term coming in. Now what's left to solve for our A of L's and B of L's is just algebra. We have 2 equations and 2 unknowns. For the L equals 1 case, here is our 2 equations, and 2 unknowns are A1 and B1. And then for the L doesn't equal 1 case, we have here 2 equations and 2 unknowns for each L, right? This is true for like L equals 5 and L equals 5. So then what we want to do next is just the algebra steps. What I've done here is I'm going to start by doing the L doesn't equal to 1 case. And so here are my 2 equations. I started with this one. I'm multiplying it by epsilon L over R so I can match this to this. So this side will end up equaling this. Once I do that, then I can set this equal to this and solve for B of L. All right, and here's my algebra. I set this side here equal to this side here. So this equal to this. And what it ends up giving me is an equation like this that only has the B of L's. And it's just like B5 and B5, B10 and B10, or whatever it is. And I can factor that BL out, and what I get is BL times some constant equals 0. And this constant is, just numbers, not 0. So that means BL has to equal 0. So I'm getting from this, if L doesn't equal 1, B of L equals A of L equals 0. So that's where I've ended up if I've looked at the L does not equal 1 terms. So that's a lot of progress, right? Because this means I'm not going to have an infinite series. In fact, all I'm going to have is the L equals 1 term. So next I want to make some space and then do this L equals 1 term. All right, so for the L equals 1 term, I'm going to try to combine these 2 equations. Oops, I copied that wrong. There, that's better. All right, so I'm going to combine these 2 equations, again, just doing the algebra. So this is great practice if you pause here and see if you can do the algebra yourself and solve for B1 and A1. All right, so here's my algebra. First, I did something very similar. I multiplied by epsilon over R to get this so that this side would equal this side. So I could set this equal to this, and that's what this side is. And then it's just a matter of solving for B1. And the only interesting thing I did here is I plugged in for epsilon, epsilon naught, epsilon R, and then I get this equation for B1. Then I really just need to go plug this back in. Maybe up here would be an easy place to solve for A1 tilde, our only other unknown. All right, so here's my algebra. I would just plug back in to this original equation here, which is also this original equation, except I divided through by r, so I could just have it solve for the a1 tilde. Right, and then easily just plug b1 in, just some algebra. This turned out to be minus 3, right, because these two cancel. And so now I have an equation for a1 tilde and for b1, and then I know all the ones that aren't 1 or 0, so I've really solved the problem. So now I just need to go back and plug in to these equations to get my final potential. So that's what I'm going to do next. Always good practice to pause and do it yourself. Here is, I rewrote the two things that we figured out just because I'm going to need to erase this later. But here's inside. I just plugged into here. We only have the 1 term, so we only have little r to the 1. We only have p1. Then we know that p1 is cosine theta. And then we know that our cosine theta is actually z. So this is what we have for the potential inside. Of course, I can always take this potential and rewrite it as an E field just by taking the gradient of V, and that we get this nice uniform field inside, much like we did with the conductor. Although you can see it's a different value of the E field. It's not completely canceling anymore. What we're getting inside is actually still some E field. And then outside, again, I'm just plugging in here with, we know everything is 0 except the 1s, and we know the value of B1 right here, and here we already found A1 at the very beginning. And so that gives us this equation for V out, again, depending on cosine theta. And then it would be a good thing to check, though I'm not going to do it, that these two equations, the one I have here and the one I have here, satisfy all three of our boundary conditions. I could go on to find the E field from this. We know from the conductor that this is very similar to the conductor, that this is really just another kind of dipole plus constant E field with just the dipole component reduced from what it was from a conductor. All right, so I picked this back up in class where we're going to talk a little bit more about the meaning of these, interpret more physically what the meaning and implications of these two potentials in this E field. But here I just wanted to go through and show you the example of actually doing the separation of variables out, the boundary value problem, step by step, but here with this dielectric boundary condition instead of the boundary conditions we've done in the past.